Hello, today I will be presenting my lab report on DC and RC circuits. The purpose of this lab is to explore how charge conservation and energy conservation dictate the behavior of resistors and capacitors in series and parallel combinations. We modeled these systems using the PHYS circuit construction kit to measure current and potential differences. As a brief preview of our main results, we verified Kirchhoff's loop rule with a net potential difference of 0V around a closed circuit loop, and we determined that the time constant for an RC circuit can be accurately modeled using exponential decay function. Let's dive into fundamental physics principles. First, energy conservation gives us the loop rule, which states that the sum of all potential differences around any closed circuit loop must equal 0. Second, the charge conservation in a steady state means that the electric current remains constant throughout a single loop series circuit. Current is neither created nor destroyed. For our system, we define the moving charges, resistors, and capacitors inside the circuit pathways. The surroundings encompass everything outside these components. Our model assumptions rely on ideal conditions. We treat the connecting wires and ammeters as having zero internal resistance, meaning no potential drops occur across them, allowing us to isolate the behavior of our targeted circuit elements. In the first part of our experiment, our initial conditions consisted of two ideal 1.5 voltage batteries placed in series, yielding a total electromotive force, EMF, of 3 voltage. We connected this to a 47 ohm resistor and a 100 ohm resistor in series. Based on the principles of charge conservation, the current must be identical everywhere in this single loop. Using Ohm's law, we predicted the current by dividing total voltage by total resistance. As seen in our simulation screenshot, the ammeters read exactly 0.02A, perfectly matching our theoretical predictions. If we reverse an ammeter connection, it simply reads a negative value because the conventional current is entering the negative terminal instead of a positive one. Next, we replaced the ammeter with a voltmeter. Interestingly, the ammeter dropped to 0A while the voltmeter read negative 3V. This happens because an ideal voltmeter possesses infinite internal resistance to prevent it from drawing current when placed in parallel. When placed in series, it acts like an open switch, completely stopping the flow of charge. Therefore, the current becomes 0, and the voltmeter measures full potential difference across the open gap, which equals the total battery voltage. When we removed the voltmeter and closed the loop with a regular wire, we measured individual potential drops. The sum of these potential differences across a full round trip around the circuit added up to exactly 0V. Confirming Kirchhoff's loop rule. The potential stays flat and the ideal wires climbs sharply inside the batteries and drops linearly across both resistors according to their resistive values. In the final section, we investigated time-dependent behavior using an RC circuit containing a battery, a capacitor, and a light bulb acting as our resistor. When the capacitor charges, current flows rapidly at first, causing the bulb to shine brightly. As charge accumulates on the plates, the opposing voltage increases, causing the current to decay exponentially to 0 and the bulb to go dark. By removing the battery and discharging the capacitor directly through a 30 ohm light bulb, we tracked the voltage over 20 seconds. Plotting ln of delta V over delta V naught against time yielded a clear linear relationship where the slope equals -1 over RC. Our calculated time constant, tau equals RC, perfectly matched with the values specified inside the simulated parameters, confirming the high predictive accuracy of our mathematical model. To wrap up, let's address two what-if scenarios. First, what if we use a real ammeter instead of the ideal simulated one? Real ammeters are not perfect. They possess a small, non-zero internal resistance. If hooked up to our circuit in real life, this additional resistance would slightly increase the total resistance of the loop. Consequently, the actual measured current would be slightly lower than our ideal model's prediction of 0.02A. Second, what if we connected a real battery directly to a real capacitor with no resistor? Our ideal model assumes wires have zero resistance, meaning the total resistance R equals 0. Plugging this into our equation, the time constant tau equals RC becomes 0, predicting that the capacitor would reach full charge instantaneously. However, this would not happen in real life. Real batteries have internal resistance and real connecting wires have small but tangible resistances. This small net resistance ensures that the circuit maintains a finite, non-zero time constant, meaning the capacitor would still take a brief measurable fraction of a second to charge fully.